calculations, and equivalent weights, which is very heavily calculations. So your next exam, expect it to be 80 of the 100 points, maybe even 90 of those 100 points being mathematical. It's going to be an extremely mathematical exam. Right? For some of you that's good, for some of you that's not, but that's the way it is. All right. But now the point I want to make is, while we're headed for exam 5, we are also inching closer to your final. And your final exam is comprehensive over the semester. It is multiple choice. And I know we talked about this once before, back when the 1120s bombed their midterm. But just to remind you, and to I guess give you an indication of how to study for that final exam, it's not to go over the things that you never understood and try to learn them. It's to go over the things that you've done well. Whatever you've got as your strengths, review those and know those perfectly and let that carry you, all right? If you've got time, then yes, definitely look at things that you've gotten wrong and try to get help to fix that. But the more important thing, the thing that's going to help your score the most, is reviewing things you already got right. Because what will absolutely kill you is, what's worked so far, maybe, is getting by on partial credit. But there's no partial credit on a color in the dot kind of test. You either color in the right dot or you don't. All right? So what may have been 9 points out of 10 on a regular test is going to be 0 out of 4 on that final. Okay, and I'm not trying to scare you about that. I'm just trying to say, go over what you've done well at and refresh. All right? That should be your primary emphasis. All right? There's some topics that you've got to look at because you know you're going to be asked about it repeatedly. That's going to be mole relationships. That's going to be electron configuration, Lewis structure type things, because we spent almost a month on Lewis structures. Well, not Lewis structures, but we went from electron configuration to quantum numbers to Lewis structures to properties that came from Lewis structures. That was a theme there for 3 or 4 weeks. So you know you're going to have a lot of that. All right? There will be things on D2L to help you with that. All right? But your emphasis needs to be on brushing up and fixing detail stuff rather than just broadly trying to teach yourself certain topics. All right? All right. Did anybody else sneak in and not get their exam? All right. Class average was 76. I don't know if Matt mentioned that or not, but class average was 76 for it. Answer key is posted. I put that up probably about half an hour ago. So that's there if you want to get that and take a look. In this next section, we're going to be looking at physical behavior of gases. Now, back when we did Lewis structures, we talked about physical behavior for solids and liquids. That was physical characteristics like surface tension, viscosity, vapor pressure, those sorts of things. And we looked at how to tell, based on a chemical formula, which ones are going to have the higher surface tension, which ones are going to have the higher viscosity, those sorts of comparisons. All right? Now we're going to be looking at physical behavior for gases. And the primary, that's awful. Oh well. I'm not buying another one of those. I'll drink it anyway. It's all I've got in here with me. We'll see. In the fancy little diagrams here, on the left, you've got a picture of a solid. Solids are easy to measure. When you go in the lab and you measure a solid, how do you do it? Grams. You weigh it, correct? Solids are most easily measured by mass. Liquids, you could do them by mass, but they kind of flow. So what's the more convenient way to measure the amount of a liquid? Volume. If you wanted to get mass, you would have to weigh the beaker, pour it in, weigh the beaker again, subtract to get the difference. And if it's not how much you want, you have to adjust, correct? But volume is convenient for liquids. Because they flow to fill a container, you take advantage of that and you measure by volume. Gases are different. Gases are an expanded state They are not bound onto each other, and you can't quantify a gas in an open beaker because it won't stay in the open beaker. You have to, by definition, the right-hand side, you've got to have a closed system. And it's not going to be so easy as just measuring one characteristic to determine how much you've got. You've got to know 3 properties to be able to quantify that. You need to know the volume of the container, because the gas is going to expand to fill all the available space. You need to know the temperature that it's at, and you need to know how much pressure it exerts. And if you are able to measure all 3 of those, then you can quantify how much gas is in the bottle. Experimentally, it's considerably more awkward to quantify a gas as opposed to your other physical states. Question about that? Reason for that comes about physical differences. When we talked about solids and liquids, it applies to liquids too, but we said that the differences in property result from differences in the molecules in terms of molecular size and molecular attraction. Some molecules are just bigger than others, and therefore they're going to occupy more space. Some particles, maybe due to hydrogen bonding or something like that, some are just simply held stronger together than others. Therefore they give you more surface tension, higher boiling points, and things like that. Solids and liquids, different substances behave differently, and it's always because of a difference in size or a difference in strength of attraction, one or the other. But see, now here's the nice part about gases. By the time you convert something into the gas phase, you overcome those differences. If we're comparing A and B in terms of which occupies more space, if we're talking solid phase, B occupies more space, correct? But by the time you convert them into gas and they expand to fill all the available volume, then the amount of space that B fills in this container and the amount that A fills in that container, they're both pretty much negligible, correct? Because the vast majority of that volume is empty space. So any kind of differences you have based on molecular size, those are out the window, because neither has a significant size compared to the total volume. So do you see that? All right. If we're comparing A and B and C in terms of differences in strength of attraction between the particles, some bound up stronger than others when they're solid, does that carry over to gas phase? No, because nobody's attached to anybody anymore, right? You can't talk about strength of B to B attractions if there are no B to B attractions. So the 2 criteria that make A different from B, different from C when they're a condensed phase like solid or liquid are negated when something is converted into gas phase. Therefore, all capitals, this is important, therefore, all gases behave the same. Now, I'm not talking about reactivity because some things react more than others, but I'm talking about physical characteristics. All gases behave the same. And so you don't need one set of equations for carbon dioxide and a different set for argon and a different set for whatever. One set works for everybody. Because in terms of the physical behavior, they're all alike. All right? Any question so far? Principles of kinetic molecular theory. These are in your book. I'm going to just talk about a couple of them here. I'm not going to list them all. And it's not important. I mean, I've made room here for 5 points. It is not important that you memorize the 5 points. All right? What is important is that you read through those and you can kind of picture what's going on. I'm not going to ask you to quote the points here. But you do need to understand the way that they move and the way they interact, right? And as long as you understand that, then you're going to be able to in your mind, imagine what's going on in all these other contexts. Kinetic molecular theory, a couple of them we've already said. First of all, there's no intermolecular attraction. Every particle is independent, and when they collide, they simply ricochet away. No intermolecular attractions. Second, molecular volume is negligible. Now, as one example of that, and you don't need to write this down, this is just an illustration, but 1 mole of water, liquid phase, is 18 milliliters. That same 1 mole of water, if you make it vapor, and this, I'm not talking about heating it up to be steam or anything, but just evaporating water at room temperature, that same 1 mole of water as vapor would be 22,400 milliliters. 22.4 liters, 22,400 milliliters. That's a lot of expansion, correct? That's an awful lot of empty volume. And if we do the math on this, if this is the total volume that the water occupies as it bounces around, this is the volume of expansion. But only 18 of that 22,400 is actually physically occupied by your particles. The rest is empty space. Then doing the subtraction here, this is 382 milliliters of empty space. And then we apply significant figures rules. What's the amount of empty space when you apply to significant figures rules? It's going to round back up to 22,400. So the actual space occupied by those particles is practically zero. It's irrelevant, it's negligible. You have random motion. And as I said before, when they collide, they simply ricochet and move on. Question about that? One more to put up here, and that's that their kinetic energy is proportional to temperature in Kelvin units. If you heat them up, they move faster. We knew that already. Back on day 1, we talked about you heat something, they move faster, you cool it down, they move slower, correct? But specifically, that was kind of vague. Now we're talking about mathematics and calculating how much faster according to temperature. It's proportional to the temperature in Kelvin units. If you double the temperature, you double their kinetic energy. So if we've got a gas at 20 degrees Celsius and we heat it up to 40 degrees Celsius, is that going to double the kinetic energy? Is that going to double the kinetic energy? No. Now, that looks like doubling if you look at it in Celsius. By the time you convert this to Kelvin, though, this is 293, this is 313. That's not much of a change at all if you look at it in Kelvin. All right? So heating this from 20 degrees to 40 degrees is going to increase your kinetic energy a little bit, but nowhere near double. All right? We've got to think in Kelvin when we're doing gas-law relationships. So that'll become a lot more comfortable once we actually start doing the math. As far as the math goes, there's really 4 gas laws that we're going to deal with. The most important, the one that you use most of the time, is called the ideal gas law. And this is your equation. This equation you do need to memorize. And it lists the units for it. Pressure is the one we've not dealt with before. Pressure is most often measured in units of either torr or what's called millimeters of mercury. MM for millimeters, Hg for mercury. The very first barometers used columns of mercury, and the pressure would make it move. And so they would measure how many millimeters the mercury has moved, and that was their indication of pressure. Torr is just renaming that unit. So the torr and millimeters of mercury are the same thing. Just know that those are interchangeable. Volume, most commonly we measure that in milliliters. That's what's convenient. The amount of gas, most commonly, that's measured in grams because that's what's convenient. Temperature in Celsius, because that's the way your thermometers are. Which leads us to an unfortunate situation where if those are your 4 variables and the units that go with them, this is the value of your gas constant. There's a proportionality constant in this equation, and it's not based on torr or milliliters or grams or Celsius. So that means we're going to have an awful lot of unit conversions to do. That's not my fault, all right? If it were left up to me, I would have used Kelvin and whatnot in the equation, but that's not the way it is. This gas constant that I've boxed in there, you do not need to memorize. That constant will be given along with the units. You need to know the formula, PV equals nRT, and you need to remember to change things into the proper units so that you can calculate and use unit cancellation on that constant. So conversions were to convert Celsius to Kelvin, you add 273.15. To convert milliliters to liters, 1,000 milliliters is a liter. We've been using that one a lot. We need to convert grams to moles. That's molar mass conversion, correct? We've been using that one a lot. And pressure needs to be in units of atmospheres, and the relationship here is that 1 atmosphere is 760 torr. We talked about that very briefly when we did vapor pressure. So 1 atmosphere is 760 torr or 760 millimeters of mercury. This is called the ideal gas law. And it's the primary one that you'll be using. Calculation number 1. We've got a sealed container, 400 milliliters volume, has argon gas in that at 900 torr and 28 Celsius, and you're asked to calculate how many moles of argon are present. First thing to do is put a label on every number that you've got. This 400 milliliters, that's a volume. 900 torr, that's a pressure. 28 Celsius, that's a temperature. You're asked for moles in your equation, that's N. So if you look at the information of what you've got and what you want, that fits rather nicely with your ideal gas law. You know volume, pressure, temperature, and you're solving for moles. With the ideal gas law, you're going to know 3 of those 4 variables, and you're simply solving for the 4th. So, here's our equation. We're solving for N, so I'm going to go ahead and rearrange this before it gets all cluttered up with numbers. Pressure is 900 torr, but I can't use that in torr. I have to convert that to atmospheres. .184. Volume is 400 milliliters. That has to convert to liters, so that's 0.4000 liters. R is our gas constant. And our temperature is 301 Kelvin. Question about any of those 4 numbers that are plugged into the equation, about where they came from. The pressure is really the only new one. Question. Then you go through the math. You're able to keep 3 significant figures, so 0.0192 moles of argon would be it. Question about that?
Where does the .0.821 come from?
That is our gas law constant, and it would always be given. So what's on the right-hand board there, the equation, you've got to memorize. But the value for R and the units that go along with R would always be given. And that's a help to you because, just for pretend here, if the temperature is 28 Celsius and I plug in 28 Celsius, then atmospheres cancels atmospheres, liters cancels liters, and Celsius does not cancel Kelvin. And that will help you catch errors before you do the math. So this part will always be given. Question? Are you getting 0.192 or something close to that? Yes? Any question about getting that? All right, work number 2 on your own. What are you getting for number 2? This one's carbon dioxide, not argon. As if it made a difference, right? Because all gases behave the same, right? It's going to be the same number. If it's the same temperature, same pressure, same volume, it has to be the same moles, correct? All gases are alike. Go ahead.
I should go like wrong on the first one.
Mm-hmm.
I was getting a liking number like 1,736 or something.
Try putting all of this in parentheses. That should take care of it. All right, let's try one that's not a trick question. Number 3. Did that take care of it? Okay. One tip on this one, but I want you to work this one on your own. We're talking about elemental oxygen as a gas. This is not oxygen in a compound. That means it's one of your diatomic elements. So oxygen in this question is O2. Go ahead and work this one out on your own. This is what each of your conversions is going to look like. To get the numbers that go in the ideal gas law. Question about any of these?
Go over them.
I'm sorry.
Will you go over them?
On how to get them?
Yeah.
You're doing molar mass to get the out of grams and into moles. This was our new conversion, converting torr into atmospheres, and then milliliters to liters. It's unit cancellation to get the numbers that would go into the gas law. 0.156 moles of oxygen, 0.375 liters, 1.05 atmospheres. So that's numbers for all your variables except temperature. Question about this being O2 rather than O. You got to know your 7 diatomic elements. We're dealing with oxygen as an independent element, so its stable form is the diatomic form. Now we convert these others out of milliliters to liters, out of torr into atmospheres. Once you have that, you plug it into your ideal gas law, which looks like this, but we're solving for T, so it looks like this. We've got P, we've got V, we've got N, and we've always got R. Now when you solve out, that's going to give you a temperature in Kelvin. It's going to automatically come out in Kelvin, and you have to convert that at the end to Celsius. I'm getting 307 Kelvin. We subtract 273 from that to get it into Celsius. And so that comes up to be 34 Celsius. Does that answer your question or not? Yes? Okay. Other question?
Does it matter if my answer comes out to be like 35?
No, that's just a difference in rounding here or there, so that's fine.